Hi everyone. Today we are going to discuss about mathematical analysis for recursive algorithms. So in this presentation we will understand how recursive algorithms are analyzed mathematically using recurrence relations. We will also study three important examples: factorial function, towers of Hanai, binary representation of decimal numbers. Let's begin. So these are the contents. Today's presentation includes four topics. First, we will learn the general procedure for analyzing recursive algorithm. Next, we will study the recursive factorial algorithm. Then we will understand the famous towers of Hanai problem. Finally, we will analyze a recursive algorithm for finding the number of binary digits in a decimal number. So it's a general plan for analysis. Whenever we analyze a recursive algorithm, we follow five important steps. The first step is identifying the input size. Second, identify the basic operation that consumes the execution time. Third, determine whether the number of operations changes for different inputs of the same size. Fourth, formulate a recurrence relation representing the recursive calls. Finally, solve the recurrence relation or determine its order of growth using asymptotic notation. These five steps help us determine the algorithm's efficiency. Example 1, factorial function. So our first example is the recursive factorial function. The factorial of a number n is defined as n factorial equals n multiplied by factorial of n minus 1. The base case is 0 factorial equals 1. Instead of multiplying all the numbers directly, recursion repeatedly calls the same function with a smaller value until it reaches 0. Factorial algorithm. So this slide shows the recursive algorithm. If n equals 0, the function returns 1. Otherwise, it returns the result of factorial of n minus 1 multiplied by n. For example, factorial of 5 becomes 5 into factorial of 4, which becomes 5 into 4 into 4, 3 into 2 into 1. It is equals to 120. The recursion stops when n becomes 0. So factorial analysis. Now let us analyze the algorithm. The input size is simply n. The basic operation is multiplication. Let m of n represent the number of multiplications. The recurrence relation becomes m of n equal to m of n minus 1 plus 1 because every recursive call performs one multiplication after returning. So since one multiplication is added to every level, so the total number of multiplication is proportional to n. Therefore, the time complexity is big O of n. So our second example is the towers of Hanai puzzle. There are three pegs. A is the source, B is the auxiliary, and C is the destination. Initially, all the disks are placed on peg A in decreasing order of size. The objective is to move all the disks to peg C following three rules. Only one disk can be moved at a time. A larger disk cannot be placed on a smaller disk. The auxiliary peg can be used whenever necessary. So this is the towers of Hanai illustration. So this figure illustrates the movement of disks between the three pegs. The algorithm repeatedly moves smaller disk first, then moves the larger disk, and finally moves the smaller disk again. This recursive pattern continues until only one disk remains. The problem is an excellent example of divide and conquer recursion. So this is the towers of an algorithm. So this algorithm works as follows. If only one disk exits, move it directly from source to destination. Otherwise, move the top n minus 1 disk from source to auxiliary. Move the largest disk to the destination. Finally, move the n minus 1 disk from auxiliary to destination. So each recursive call solves a smaller version of the same problem. So this is a towers of Hanai analysis. Let m of n represent the number of moves. The recurrence relation becomes m of n equal to 2 into m of n minus 1 plus 1 because the first recursive call moves n minus 1 disk. One move transfers the largest disk and the second recursive call again moves n minus 1 disk. Using backward substitution, we obtain m of n equal to 2 power n minus 1. Therefore, the algorithm has big O of 2 power n time complexity. So this means the execution time doubles whenever one more disk is added. The next example, binary representation. So the recursive idea is simple. Continuously divide the number by 2. So each recursive call removes one binary digit. When the number becomes 1, the recursion stops. So the algorithm checks whether n equals 1. If yes, it returns 1. Otherwise, it recursively calls the function with floor of n divided by 2 and adds 1. For example, for n equals 16, the recursive call become 842. The number of recursive call is 5, which equals the number of binary digits.